welcome to video tutorial 2 in the Albatross Flight Dynamics Lab. In this one we're going to look at the components of the flight dynamics simulation environment and how to conduct different experiments. So now let's have a look at our aircraft in the scene view, and we're going to go down the hierarchy on the left hand side here in the hierarchy window to understand how this model's been put together. And at the very top here, top left, we've got the aircraft model, and the very first node in this kind of tree of objects is the aircraft rigid body, and this is where we store the mass information of the aircraft. So here it's set at a mass of 7 kilograms and we've got gravity applied. And then underneath this node we've got various other bits that hang down from the kind of mass node of the aircraft. So we've got the geometry there, which is essentially the CAD model of the aircraft, and that's really there for people to see the shape of it and draw reference in terms of where things are. From terms of the physics, it's not controlling the physics. The physics is controlled by our inertial bodies we put on and our aerodynamic bodies. Then we get to this blue thing here, which is the mean aerodynamic chord. And if you've done any work with flight dynamics, you understand that the mean aerodynamic chord is the kind of critical reference length or position on the aircraft. And it's essentially kind of the average chord of the wing as far as the aerodynamics is concerned. And so the core-to-chord point of this mean aerodynamic chord is where we can assume the lift is working at reasonably low angles of attack. And so all the setup of the aircraft in terms of centre of gravity and the like is all referenced relative to this mean aerodynamic chord. And the way the geometry is set up is that the aircraft is in the world there, and this is the 0 for the aircraft, and we're in world coordinates here where Z is forward, X is to the right and Y is up, but the leading edge of the mean aerodynamic chord is then set at minus 41 or 40 odd centimeters back from the nose, so that's 40 centimeters. You put a ruler on it, but then we've done a slightly cunning thing of we've switched round at 180 degrees in the Y direction now, so this Z positive is going this way, and what this means is now that this coincides with the way flight dynamics distances are measured. In a sense, it's positive aft from the leading edge of the mean aerodynamic chord. So there's a simulation world, and then in this world here, in terms of the mean aerodynamic chord, it's been set up so that it corresponds with your understanding or the textbook understanding of how flight dynamics things are measured. Okay, so then after that we've got our centre of gravity, and this is because it's underneath the mean aerodynamic chord here, means that everything's measured relative to it. So I can pull this backwards and forwards, and if I place this towards the front here, we can see the Z coordinate up here, so that's now 2 millimeters aft of the leading edge of the mean aerodynamic chord. And remember, if you want to see things lined up properly, you can use the orthographic projection, and so now we can see precisely where the leading edge of the mean aerodynamic chord, so that's pretty much on the money, and then we could set that to say a quarter of the way back. So this is the mean aerodynamic chord length is around 24 centimeters, so around 7 centimeters is about quarter chord of that, and just kind of eyeballing that, our centre of gravity there is at about quarter chord of the mean aerodynamic chord. Measuring things in simulation is actually quite easy. When you've done this in real life with a ruler on an aircraft with no flat surfaces or anything else, you realise how hard it is, and actually having a digital model of an aircraft where you can move things around is a much more convenient way of dealing with geometry. But ultimately in real life you have to check it against what it is in physicality. Okay, so what else we've got? We've got the undercarriage. So that's the main gear, rear axle. Go back into flat mode again, so that we can see there that the gear is placed behind the centre of gravity at the moment. And if you remember, the choice of the centre of gravity is about aerodynamic stability, but also you have to make sure that your wheels are placed in an appropriate place so that the aircraft is balanced on the ground. One thing you'll notice in a later video, the distance of the the wheel axles is slightly different It's been upgraded since last year as we got some new undercarriage, so just check the actual location of the Z distance of the undercarriage when you're doing your balance to work out where the CG is. Okay, so that's the kind of mechanics of the aircraft in terms of mass and where the wheels are. In terms of aerodynamics, you don't really have to worry too much about that. This is kind of provided. I'm going to turn gizmos on now, and those blue boxes you can see there are the kind of aerodynamic panels used to model the aircraft. It's done using blade element, and there's 4 panels on the wing and 2 panels for the tailplane, and they're scaled so that the area of the wing is right and the center of the panels is right, and the angle of the panels is right, so this thing has the right wing loading and the orientation of all the surfaces is correct. So it's a relatively simple aerodynamic model, but it's accurate at low angles of attack in terms of the trim angles and the like, but it carries on working at whatever angle, so if you stall it or fly it backwards it still works as well. So that's the wing, and if we now tailplane fuselage. Now if we look at the flight control surfaces, so I click on those, they're highlighted in grey. So we've got our ailerons, and we've got 2 flaps, and we've got our elevators or ruddervators, whatever you want to call those things, at the back. Propulsion, that's our propeller. The stuff in there, those green things are colliders which are used to set the moment of inertia of the aircraft, and they're also the bits that if you hit the ground that it bounces off those, so that's how the kind of physicality of the model is provided. There is some smoke particles on the wingtips which we can use, and then there's a camera on the front. Okay, so that's the model. If we now go to the Flight Dynamics Lab Manager, and this is where you run experiments, and the way to do this, so select the settings for your experiment here, and if you click on the little target icon there, it'll open up this window and you can choose what experiment you want to do. So the next one you will be doing actually is weight and balance, so if you click on that it will go to the weight and balance experiment, and if we wanted to do something like the dynamic control response, we can move it to that. You can set the center of gravity for each of these experiments. The way they're set up, they're kind of reasonably sensible, so you don't actually need to change any of those things, so it should just work off the bat. Next up is the aircraft manager, and this is where we set the parameters and set up the controls for the aircraft. Wind manager, where you can control the wind speed. When it's on a gimbal testing, it's quite interesting to see as you vary the wind speed, you can vary the direction and the elevation of the wind as well. For most of the flying you're doing, the wind doesn't necessarily come into it, but this is useful when it's kind of stuck on a pole and you're throwing wind at it to do your dynamic experiments. Data loggers, in terms of recording information, the only one you need to know about is the static wind tunnel. And this is kind of pretty much set up for you, so you don't really need to do anything. But what this does is allows you to set a range of CG positions, a range of control deflections, flap deflections, and it will just go through lots and lots of experiments to measure the forces and moments on the aircraft. So a bit like what you do in a wind tunnel, where you do a series of traverses of different parameters, this will just go through and do them all. It does it really quickly, so you can't really see what's going on. You can actually slow it right down, and then you can actually see what it's doing as it's going through it. So that's kind of fun to just see in terms of all the variations you do. You can see it going through it, and those numbers will be stored in a text file which can then be opened in Excel. Okay, last thing we've got is the model of the environment. So there's the hangar there. And then we've got Lambeda, and if we zoom out to that, there's a kind of a topo map of Lambeda, and it's reasonably accurate in terms of heights and everything else. The ground sampling is pretty chunky, but it's an accurate map in terms of the heights and everything else. The airfield is about 5 meters above sea level. Okay, and then we've got some other scenery. There's some pylons there around the airfield. Flight instruments looks a bit weird when you see it in the scene view, but that there is what the camera is seeing when you're running the game, and this is a kind of your basic artificial horizon. You've got RPM there, so from 0 to 100% of the engine, and there's some things in there, and the angle of attack, G loading, and some max and min and so on there, and it'll tell you when the flaps are down. Okay, so what we've seen is how to navigate your way around the aircraft model in the hierarchy view here, starting off with the aircraft rigid body. We've seen how to move things like the center of gravity around relative to the mean aerodynamic chord, so we can set up our flight dynamics experiments, something about how the aerodynamics is modeled on the aircraft, flight control services, propulsion. And then crucial things here, Flight Dynamics Lab Manager is where you change your experiments, and the Aircraft Manager is where you change your aircraft. Okay, and in the next video what you're going to be doing is doing a ground test on the aircraft to establish where the center of gravity is based on reaction measurements from the undercarriage.